Welcome to our course on quantum mechanics, the physics of the microscopic world. I'm Ben Schumacher. I'm a professor of physics at Kenyon College in Ohio, and I'll be your instructor for this course. In this course, we are embarking on a journey to a distant world, a world that is governed by strange and unfamiliar laws. By distant, I mean a world far from our everyday experience. I mean a world that is distant not in space, but in size. It's the world of the microscopic world. So how small do I mean by microscopic? In fact, I don't mean something you can see in a microscope. I mean something far smaller than you can see in an ordinary microscope. The characters of our drama are entities like atoms and subatomic particles such as electrons and protons and neutrons. Other characters of our drama include photons, which are the particles of light, and these are all exceedingly small. So how small is small? How small is an atom? Well, I have here a 1-inch cube of aluminum. It's 1 inch long, 1 inch high, 1 inch wide. And in 1 cubic inch of aluminum, there are 10 to the 24th power aluminum atoms. 10 to the 24th power. A 1 followed by 24 zeros. That's 1 trillion aluminum atoms. There are 100 million aluminum atoms on this edge, 100 million aluminum atoms on this edge, 100 million aluminum atoms on that edge. About 100 million aluminum atoms to the inch. That's a lot. Well, what about something you actually could see in a microscope? How about a single-celled organism? Well, a typical single-celled organism contains about 1 trillion atoms. A 1 followed by 12 zeros, 10 to the 12th power. Okay, I've been throwing around the number 1 trillion. How big is a trillion? Well, imagine how big a grain of fine sand is. Now imagine an entire large truckload of sand. That turns out to be about 1 trillion grains of sand. Or here's another way of thinking about 1 trillion. Imagine how many heartbeats you have in a day, distinct heartbeats. That's not actually a very big number. It's only 100,000. Well, maybe that is a pretty big number. 100,000 heartbeats in a day. Now imagine the entire population of New York City, about 10 million people. That means that there are about 1 trillion human heartbeats in New York City in the course of a day. So 1 trillion is a really big number. And there are 1 trillion times 1 trillion atoms of aluminum in this cube of aluminum. Okay, so atoms are pretty small. What about photons? How big are photons? Well, to do that, let's consider an ordinary light bulb, like this one. An ordinary 20-watt light bulb emits about 100 million trillion photons in 1 second. 100 million trillion. That's 10 to the 20th power. A 1 followed by 20 zeros. That's the number of photons that come out of a 20-watt light bulb in a second. These are huge numbers. Atoms, electrons, and photons are extremely small compared with our everyday experience. And quantum mechanics is the basic physics of this realm, the realm of atoms, electrons, and photons. Now, the microscopic realm is not just a miniature copy of the world of our experience. If that were true, this wouldn't be that interesting a subject. But in fact, in the microscopic realm, there are lots of surprises. And we'll talk about things that will at first be hard to believe, but are nevertheless true about the microscopic realm. But I want to emphasize one important fact. The quantum world is nevertheless our own world. The quantum world is the world we live in. And quantum mechanics will explain not just funny things about atoms, but will explain basic facts about the world we see every day. Okay, what is quantum mechanics? Let's take that apart. First of all, what is mechanics? Mechanics is the branch of physics that studies force and motion, how things move, why they move, the laws governing motion in the world, the way things in the universe evolve over time. That's all mechanics. Now, there's a kind of mechanics called classical mechanics. Classical mechanics is the theory of mechanics based on Newton's laws of motion, developed by Isaac Newton in the late 17th century. And classical mechanics is a branch of a somewhat larger realm called classical physics, which also includes other subjects such as thermodynamics, which is about heat and energy transformations, electromagnetism, which is about the physics of electric and magnetic fields, optics, which is about how light propagates. All of these are branches of classical physics. And classical mechanics is sort of at the center of classical physics. For more than 200 years, classical mechanics was the best theory of physics, the gold standard of theories, far-reaching and extremely precise. If you wanted to know how to predict where a projectile would land, or how to build a strong bridge, or how the planets were going to move 1,000 years from now, classical mechanics was the tool you would use to figure that out. And until about the year 1900, the entire story of physics was largely the story of the success of Newtonian mechanics. However, around 1900, it became clear that classical physics could not explain the behavior of the microscopic world. Classical mechanics wasn't enough. And so quantum mechanics was the new theory developed to replace Newton's laws, and especially to account for microscopic pieces of matter and how they behaved, but also to account for puzzles about the world that we could see and touch with our ordinary senses. It was called quantum mechanics because in this theory, energy was found in many circumstances to come in distinct lumps, distinct packages, or quanta of energy. That's the quantum in quantum mechanics. Now, the first quantum ideas were proposed around 1900. But the theory itself was not fully developed until the 1920s. So quantum mechanics was not constructed in a day. The process of its discovery was a remarkable process with many steps, and we'll talk about that process. There are two other terms I want to explain. I'll use the phrase quantum theory. Sometimes I'll say quantum physics. Now, technically speaking, quantum mechanics, quantum theory, quantum physics are not quite the same thing. Each term is a little more encompassing than the last. But for our purposes, we can regard them as near synonyms for quantum mechanics. I'll use one or the other just for variety's sake. So don't worry about the distinction. Quantum mechanics is now the most successful theory of physics ever devised. Some phenomenon explained by quantum mechanics are, and we'll discuss all of these, the basic internal structure of nuclei, atoms, and molecules. We understand that structure because of quantum mechanics. Quantum mechanics explains how light is absorbed and emitted by matter, a very important subject. Quantum mechanics explains how solids and liquids behave, especially at very low temperatures where their behavior can be quite surprising. Quantum mechanics is also the theory that accounts for how elementary particles interact with each other. So quantum mechanics has a tremendous range of applicability. Even though The basic quantum ideas are now more than 100 years old. Even though quantum theory or quantum mechanics itself is more than 80 years old, quantum theory remains the basic framework within which modern theories of physics are framed. It's the basic language of physics. For example, superstring theory, which is an exciting but speculative theory of elementary particles and forces. Superstring theory is a quantum theory. Now, our course is not going to cover superstring theory, but I just want to point out that all of these modern theories, like superstring theory, are encompassed in the general framework, the same general framework that has been around for more than 80 years. So this course is not going to only be concerned with this revolutionary development of quantum mechanics in the years 1900 to about 1930. This course is going to be also interested in developments in quantum mechanics since that time, right up to the present day. Okay, this tremendous success is only one side of quantum mechanics. What really makes quantum mechanics interesting is that it is also, without a doubt, the strangest and most surprising theory of physics ever devised. The laws of the microscopic realm challenge our imagination. It is a wonderful adventure to try to come to grips with the quantum world. So some of the weird implications of quantum theory that we'll discuss all of these that I mentioned, are as follows. Let's see, the first one, quantum mechanics tells us something very strange about the laws of probability. Quantum mechanics tells us that different possibilities can cancel each other out in a way that you never would have expected. So suppose a particle could go from here to here, this point to this point, along two different routes. It could go this way, it could go this way. There are two possible routes, and each route in itself is possible. In quantum mechanics, it can turn out that if both routes are allowed, it's actually impossible for the particle to go from here to here. Each route is possible, but together the possibilities cancel out and the whole thing is impossible. That's completely strange. Another really strange idea in quantum mechanics is just the whole way that individual particles move through space. It's not that quantum mechanics is just a new theory of motion. It's not just a refinement of Newton's laws of motion from the 17th century. No, quantum mechanics is a new theory of what motion means. In quantum mechanics, particles don't move along definite paths through space. Particles travel through space in the form of waves that spread out and are many places at once. It's very strange. Another strange aspect of quantum theory is what it tells us about how groups of particles act together. It turns out that two quantum particles can actually be exactly identical to one another, more alike than two pennies, more alike than identical twins. They can be exactly identical to each other in all of their properties. Now that may seem like a kind of a minor point, but it turns out that this fact, the fact that particles can be identical to each other, two electrons can be exactly the same, that fact has gigantic implications for the world that we see every day. And we'll explore that very strange aspect of quantum theory. Another strange aspect of quantum theory is quantum entanglement. For my money, quantum entanglement is the strangest thing in this strange old world. Quantum entanglement is a phenomenon that was first studied seriously by Albert Einstein back in the 1930s. Albert Einstein called it spooky. And it's a good word because quantum entanglement is a kind of strange interconnectedness that can exist between two particles even if the particles are far apart. When the particles are observed or interact, they do so in a way that almost seems as if the particles are conspiring together at a distance to make it work out. So quantum entanglement is a very, very strange thing, and we will certainly discuss that at some length. Quantum mechanics also tells us some really strange, new, and remarkable things about the properties of energy. Quantum mechanics tells us, first of all, that energy comes in discrete amounts, the quantum in quantum physics. And that's very different from the old classical physics, in which energy was continuous and you can have any quantity of energy. No, in quantum mechanics, very often you can only have this amount or that amount and nothing in between. That's the quantum in quantum physics. But that's not the only surprise that quantum mechanics has to tell us about energy. Quantum mechanics also tells us that there is energy present even in empty space. Even when there are no particles, even when there's no light shining through the space, even in empty space, in the vacuum, there's energy. And so quantum mechanics not only changes our view of everything, quantum mechanics also changes our view of nothing. Quantum mechanics also tells us some very strange and surprising things about the behavior of information. Now, this is a contemporary topic in quantum theory. This is a subject of research going on right now. And in fact, it's my own research specialty. It's the subject that I'm passionate about. And so I want to tell you about that during this course. In the quantum realm, information is stored and transmitted and processed in really weird ways that run counter to our intuition. What's the significance of this? Well, it may be that the weird quantum information properties could lead to powerful new technologies for communication and computing. We may be able to build quantum computers that solve certain problems in bizarre ways. That might happen. But it certainly does lead, considering information certainly does lead us to powerful new insights into quantum physics. And of course, that's our business here. Okay, you can see with all these many strange aspects of quantum theory that quantum physics has inspired profound philosophical debate. I mean, quantum mechanics is such a surprising set of assertions about the world. What does it all mean? How can the world be like that? And these philosophical questions are also an important part of our story. We're going to talk about how Albert Einstein and Niels Bohr, two of the founders of quantum theory, carried on a famous debate for years during the early years of quantum mechanics about what the meaning of quantum mechanics might be. Now, Einstein was the quantum skeptic. He thought that there might be something wrong with quantum mechanics, or that quantum mechanics might be only an incomplete description of nature. Bohr was the quantum champion. He defended quantum mechanics against Einstein's criticisms. And however we conclude that this argument came out, the argument between Einstein and Bohr forced physicists ever since to sharpen their concepts to deal with the weird nature of quantum physics. Another subject of philosophical discussion has been quantum entanglement. Quantum entanglement was kind of a leftover issue from the Bohr-Einstein debate. Bohr and Einstein discussed it from the 1930s on, but afterwards, decades later, after Bohr and Einstein had both passed on, it was quantum entanglement that most dramatically showed the deficiency of our common sense views of the world. It was quantum mechanical entanglement that showed us that the ideas about the world that you're born with simply do not apply to the microscopic realm, that the quantum world is even stranger than Einstein and Bohr realized. Now, even today, there are competing ideas about how to interpret quantum mechanics. Every physicist knows how to work the mathematics of quantum mechanics. Every physicist knows how to use quantum mechanics to calculate the expected outcome of an experiment. But what physicists do not agree on is what quantum mechanics is telling us about the nature of the universe at the fundamental level. And there are three very important schools of thought in interpreting quantum mechanics. The first is Bohr's Copenhagen interpretation of quantum mechanics, so-called because it was sort of originated at Bohr's Institute for Theoretical Physics at the University of Copenhagen. And in the Copenhagen interpretation, quantum theory only tells us probabilities. Quantum theory says nothing about what will actually happen, it only computes the odds. And the Copenhagen interpretation says no deeper view is possible. Now, since the Copenhagen interpretation, two further interpretational frameworks have been constructed. And one of these is the so-called hidden variables interpretation. And in the hidden variables interpretation, the results of experiments are really predetermined by some hidden factors that we don't know. The probabilities of quantum mechanics simply reflect our ignorance of these secret variables that are going on in the system. Probabilities, in other words, reflect ignorance. But there's something funny about that. That sounds like a common sense view, but there's something funny about that, because in order to account for quantum mechanics, the hidden factors in this interpretation can't be simply a few hidden pieces of information about this particle and that particle. The hidden factors cannot be localized in space. The hidden factors must be part of a hidden order that spans the whole universe and makes quantum mechanics work. That's what you have to believe in to believe the hidden variables interpretation. And finally, there's the many worlds interpretation, which has gained, I think, more adherents lately, but is also very strange. In the many worlds interpretation, in an experiment, no one possibility is ever really chosen. Let's suppose we have an experiment in which the particle might go this direction or that direction. And quantum mechanics predicts that each of those occurs with a 50-50 probability. In the many worlds interpretation, it's not the case that one of these things is actually chosen. The particle doesn't go in one direction. The particle actually goes in both directions. Everything happens in different so-called branches of the universe. Now, we might find this a bit of a challenge, because actually we see the particle go one way or we see it go the other way. But that's just because we too are part of the universe. We also divide. In one branch of the universe, the particle goes this way, we see it goes this way, I report to you that it goes this way, and so on. In the other branch of the universe, the particle goes that way. We see that it goes that way, I report to you that it goes that way, and so on. We're all part of the branching of the universe. In each branch, we only see one thing happen, but the entire universe contains all of these possible worlds. That's the many worlds interpretation. So it seems inescapable that any way we interpret quantum mechanics, we're going to have to come to accept something very strange about the world. All right, what's the structure of this course? Well, the course is roughly divided into a few sections. In section 1, lectures 2 through 7, we're going to talk about the development of quantum theory between about 1900 and 1930. We're going to do a historical review of how quantum mechanics was discovered. We're not going to quite do it in chronological order. We'll skip around a little bit, but I think it will be clear how we're putting the pieces together. Then, in section 2, lectures 8 through 10, we're going to actually learn some basic quantum theory. We're going to learn the abstract symbolic language that physicists use to describe the microscopic world. That's going to be an ambitious task, but we'll take it on in lectures 8 through 10. Then there's section 3 of the course, running from lecture 11 to about lecture 18. And section 3 of the course is a tour of the quantum world, a sightseeing tour with stops at the theory of identical particles, at quantum entanglement, at the physics of the vacuum, at the laws of elementary particles. We'll view how quantum theory that we have that we have learned in Section 2 applies to all these different aspects of the physical world. Then we'll move on to Section 4 in the course. Section 4 in the course will be from Lecture 19 to Lecture 22. That's the one I'm looking forward to. That's where we're going to talk about quantum mechanics and information. We'll talk about some of the most recent ideas in understanding the quantum world, how the concept of information, which is a very modern concept, a concept that's really only come along since quantum mechanics has been invented, helps us to clarify and understand the many peculiar properties of the quantum world. And then, finally, Section 5. Lectures 23 and 24, the last two lectures of the course. And in Section 5, we'll venture into philosophical issues, implications, questions, and speculations about quantum theory and what it says about the nature of the world. Okay, so before we start off, we need to set some ground rules for our course. Some general expectations that we might have for the course. And the first issue that I want to mention is the issue of simplification. And I'm just going to confess to you now that we will often simplify our discussion to get at the fundamental principles. We'll leave out details or complicating factors and present a simplified version of things. We'll try to be honest. We'll try to note when this happens. Now, you as the student shouldn't worry about this. Our project is to come to